Hello everyone, welcome back to MP Coding. Today, we're going to talk about the private data field in a Linux device driver. In the last video, we covered the basic file operations. That video ended up being a bit long, so I decided to make a separate video just for this private data topic. So, if you haven't watched the previous video yet, please pause here and check that one first. Alright, let's get started. First, I'm going to move these files into a new folder called 01_file_ops. Move the files. Next, inside this directory, I'll create another folder called 02_private_data. Then I'll copy the same files from the previous example and paste them into this new folder. Now, let's open the source file. Here, in the last video, we created a global memory buffer to store data coming from user space. Now, I want to show you how private data works instead. First, let's edit the open operation. Remove these lines. No need of those print statements. If we look at the file struct, we can see that it contains a field called private_data. And if you check its definition, you'll notice that it's a void pointer. Since it's a void pointer, this means we can attach any data structure we want to this field. So here's what we're going to do. Just like before, I'll allocate memory for a char buffer, but this time it will be per file private data, not a global buffer. Create a character pointer called buffer and allocate memory using kzalloc. Pass the same buffer size as before, which is this dev buffer size, set to 64 bytes. And use the gfp_kernel flag as before. This kzalloc not only allocates memory, but it also initializes that memory to 0. After the allocation, we always need to check whether it succeeded. If the buffer pointer is null, we return a no memory error. Now, I'll attach this buffer to the file's private data field. That's how we can allocate the private data field. You can use any data structure here, but for simplicity, I've just allocated 64 bytes of memory. Finally, I'll print a kernel log message to confirm that the memory was allocated for the private data. As you know, any memory we allocate must be freed after we're done using it. So, in the release file operation, I'm going to free the memory that we allocated for the private data. If you look at the function parameters of the release callback, you'll see that it receives a pointer to a file structure. What we can do is retrieve the private data pointer from this file structure. So I will create a character pointer and assign it to the private data field. But remember, private data is a void pointer, so we should explicitly cast it to a char pointer. Now, if this buffer pointer is not null, we can safely free the allocated memory. In kernel space, we use kfree to free memory, which is similar to the standard free function in user space. Finally, I'll update the log message to confirm that the memory was freed and the file was closed. Now we allocate the private data when the device file is opened, and we free that memory when the device file is closed. Now, I'll remove the previous global memory buffer. Here in the init function, I'm going to remove that memory allocation. Alright, now let's look at the read operation. At this point, we no longer have the dev_buffer pointer, since we removed the global buffer. Here, in the read function parameters, we receive a pointer to a file structure. So we can access the private data field from here. What I'll do next is create a local character pointer called dev_buffer and assign it to the private data, casting it to a char pointer. If the dev_buffer pointer is null, that means something went wrong, and we should treat it as an error. So in that case, we simply return an invalid argument error. These same applies to the write operation as well. So I'll copy these lines and paste them at the top of the write function before we use the buffer. So now, I'm simply getting the buffer from the private data field and using it in the read and write operations. This is not the ideal approach, but I want to show you something important first. So let's build the driver. Navigate to the project directory, type make, and press enter. Okay, the build completed successfully. Next, I'm going to update the test program. I'll open the test1.c file. And then I'll remove all of the multiple open and close sections, except for the first one. Now, change the file's open flag to read and write mode. Here, after opening the file, I'm going to call the write function. The write function requires the file descriptor, so we'll pass fd as the first argument. Second parameter is the data to write. I'll take it from the second command line argument passed from the terminal. As third parameter, we need to pass the length of the data we're writing. Since we're passing a string, we can use the strlen function for this. To use strlen, we need to include the string.h header file as well. Here, the write function returns the number of bytes written. If the write operation fails, it returns -1. So let's create a new size_t variable to store the return value. After that, we'll check whether the returned length is negative. If it is, that means an error occurred, so we print an error message. Failed to write. In this case, we also need to close the file and return, so I'll add a label called close_fd above the file close section. Then, from here, I'll jump to that label using goto. If the write operation succeeds, we print how many bytes were written. Next, before moving on to the read operation, I want to pause the program. We can wait for user input using getChar. Before that, I will print the message, press enter to continue. Now let's add the read operation. Just like before, the read function expects 3 arguments. First, the file descriptor. Second, a buffer to store the data we read. So here I will create a character array with a size of dev buffer size, which is 64 bytes. I will define this at the top of the file. Now pass char buffer as second parameter. And third, the number of bytes to read. Just pass the buffer size. Now, the read function also returns the number of bytes read. If the return value is negative, that means an error occurred, so we print an error message. Here, jump to close_fd section. If the read operation is successful, we print how many bytes were read, and we also print the buffer contents. This helps us verify whether the data was read correctly. Okay, the test application is finished. We've simply added the write and read operations between the open and close calls. Let's build the test1.c file. Type gcc test1.c and press enter. It builds successfully without any errors. Before loading the module, I'm going to open the d-message buffer in this terminal. This allows us to see the kernel log messages as they appear. Now, let's insert the module. Type sudo insmod my_cdev_ko and press enter. The module is now loaded. And if we check the dev directory, we can see that the my_cdev0 device has been registered with major number 236. Now let's run the test program. Type sudo./a.out. Then pass the device file node, /dev/-cdev0. And the string you want to write to the device, I will pass hello world. And hit enter. You can see that 11 bytes were written to the device's private buffer. If you look at the offset value, it's now 11, which is expected because we wrote 11 characters. Now, press enter to continue. You'll notice that no bytes were read. The read count is 0. This happens because the offset was not reset and is still at 11. In both the read and write functions, the offset is not being reset because we did not close and reopen the file. In this situation, we actually don't need to update the offset at all in both of the read and write operations. So I'll go ahead and remove the offset updates from both the read and write functions. Also, since we're now working with per-file private data, we don't need to check the offset in this case. So I will remove these offset prints. Here, I'm going to remove the offset check. Since we're now just reading the data stored in the private data buffer, we don't need to worry about the file offset anymore. We simply read whatever is currently inside dev_buffer and return it to user space. Remove this add offset. We simply return all the requested length. Here in the write function, we no longer need this offset-based check. That logic was required earlier because we were tracking the file offset and trying to prevent writes beyond the buffer using offset value. But now, since we're writing directly into the private data buffer and we're not using the offset anymore, this extra logic is unnecessary. Instead, we'll just add this simple size check. We make sure we never write more than the buffer can hold without dealing with offsets. Remove these offsets also. Okay, now the code is cleaned up. Let's load the module again. Before we do that, we need to remove the previously loaded module. Type sudo rm mod my_cdev and hit enter. OK, module is removed. Let's clear the terminals first. Now type make and press enter to build the module source file again. OK, in this terminal, I'll open the D message buffer so we can see the kernel messages. Now let's load the module. Sudo insmod my_cdev ko. The character device is now registered, and the device node has been created in the dev directory. Now let's run the test program again. Sudo ./a.out/dev/my_cdev0. String to write, I will give welcome to MP coding, and hit enter to run. You'll see that 19 bytes are written to the private data field. Now, press enter to continue the test. You'll see that 19 bytes are read back from the device, which means everything is working correctly. Now let's open 2 instances of the device. Here, I'll open a new terminal. In this terminal, I'll run 1 instance of the test application. In the other terminal, I'll run another instance, but this time with a different message. You can see that both device files are opened at the same time, and each one maintains its own private state. If we continue the test, you'll notice that the data in each instance is managed separately. That's how we can allocate private data for the device when it's opened, and then free that memory when the device is closed. In the previous video, we used a global memory buffer. That memory is allocated when the module is loaded and stays allocated for the entire lifetime of the module, even if the device is not actively being used. With the private data approach, the memory is allocated dynamically when the device file is opened, and it is freed as soon as the file is closed. This means each open instance of the device can have its own private buffer, and memory is only used when it's actually needed. Because of that, this approach is more memory efficient, more scalable, and is generally considered better practice, especially when multiple processes may access the device at the same time. That's it for today's video. Today, we discussed the private data field and how it can be used to manage multiple instances of a device independently. In the next video, we'll talk about I/O control implementation for a device file and how we can use it to add more advanced control features to our driver. So stay tuned. Don't forget to like, share, and subscribe. I'll see you in the next video.